So welcome to the first 2016-17 academic year College of Pharmacy college-wide seminar. So it's a pleasure today to welcome Dr. V.A. Shiva. And so I think you've seen the signs around and you know from that a little bit about him. He is certainly not a typical pharmaceutical scientist for our college-wide seminar. And that's sort of part of the reason that, to me, he was really an attractive invitation. So he has 3 engineering degrees from MIT, a bachelor's degree, a master's degree, and a PhD in systems engineering, and an additional degree in visual sciences. And he's also got a pretty interesting life story that you'll hear about, including that at the age of 14, he did something pretty extraordinary. I think he'll tell us about that. And so I think there's really several aspects to his story and why I felt like he was a great individual to come. And one of those is sometimes to do really interesting and great things, you have to think a little bit outside the box. And so he's a systems engineer, and so he sees this thing that we all spend our time thinking about, the human body, as a system to be solved from an engineering perspective. So he's thinking about the same things we are, just in a slightly different way. And so tomorrow he'll be doing a seminar for the Informatics Institute at 11:30, and the room number is on the sign. So hopefully you'll go to that. That will be his more scientific presentation. But today he's going to sort of tell us a little more about a journey and about how sometimes you need to take a path that's a little different. You need to think big, and you can have an opportunity to do some really amazing things. So in addition to his academic credentials, he's won a number of awards. I'm just going to list a few. So he's been a Fulbright Scholar, Westinghouse Science Talent Honors Award, nominated for the U.S. National Medal of Technology and Innovation. He holds an interesting patent that has been placed in the Smithsonian for its historical significance. And he's currently the founder and CEO of Cytosol, which is where sort of the drug piece comes into play, which is a company that really emerged out of his discoveries that relate to really systems thinking and using a revolutionary approach to think about how to think about and solve biological problems. So with that introduction, welcome.
Thank you. All right, can you guys hear me? Is it loud enough?
Yeah.
Okay. Thanks very much. I think you guys are very fortunate to have someone like Julie Johnson in the leadership here. And I say that because, I'm in sort of the center of high tech in Cambridge. When I came here last time, it was really cool to see this focus on, I think, systems pharmacology, right, that you guys had here, had held here. And I think more importantly, for me to share this story with you, I hope what I want to inspire in you is, the talk is you are the revolution. Yes, group thinking is important as us as individuals, but ultimately everyone here has a very, very important story. Your journey is very different than mine. And what I'm going to share with you in the next, hopefully, I'm going to probably take 30, 40 minutes and hopefully leave enough time for questions, is probably my journey. But my journey is not that different than yours. And what I want you to start thinking about is, as you hear about what I'm going to share with you, that you ultimately realize there's some universal themes, which are really about where does innovation come from, who's creative, who isn't, who's determining these issues about creativity, about the sources of innovation. And ultimately, for me, I was forced into sort of understanding systems thinking because of the world that I came from, because I was trying to find some truth and universal understanding. But what I want to, hopefully, you'll get out here, I think the next talk is going to be more science-based, but this one's going to be sort of personal and science-based. But hopefully, what are systems? How systems work and why we need to take a systems approach to health. And my journey begins in India. I was born in India. Anyone been to India? 1, 2. Okay, 2 people. It's interesting. More people should go there. Okay, obviously you're there. But India is a country within countries. So even in Bombay, where I grew up, it's like an industrial furnace if America's a melting pot. You have every religion, every caste, every race. Everyone sort of lives and plays together. I mean, this scene sort of describes India, right? You have a bullock cart, you have probably a Mercedes-Benz, you have people in Armani suits, everyone's sort of flowing together. But I also grew up not only in the city, but 80% of India is villages. So most Indians who are in the cities now don't go to the villages, but I also grew up in a deep South Indian village, which the scenes are very different. And, these are the kind of sort of scenes you get. This is sort of a temple. And in that village, my grandparents were poor South Indian farmers. My grandmother actually planted rice. You'd get leeches on her, work 16-hour days. But the other career that she had, and that's a picture of her in her Sunday best, but she also was trained in traditional systems of Indian medicine. When she was in Burma, she learned, and in India, she learned. And there's a whole system that we would probably think is all woo-woo medicine, okay? Or we don't understand it, so we think it's sort of snake oil. But there's a whole, and this sort of diagram sort of simply captures it, where you have the notion of nothingness or unmanifested reality, purusha, which gives rise to prakriti, which gives rise to the gunas. The only reason I'm saying these words is there's a whole lingua franca that they have of describing existence, which goes all the way up to the notion of dhatus, are called tissues, and what we call the body. And this is just sort of the beginning of it. So in that world, people diagnose, they treat, they have their own form of personalized medicine. So I saw my grandmother, as a child doing this work. But more importantly, she also taught me, she would tell me great stories. Stories are very powerful. Of the Ramayana, which is a great epic story of this great hero who fights this great villain. And, he has this friendship with this camaraderie. But it's a story of righteousness, good versus evil. But my grandmother, as she was telling me these stories on weekends, she would have people would come to her and she would observe their face. There's a whole Indian treatise, several thousand pages, called Samudrika Lakshanam, which says that the face reveals different dysfunctions in the body. Again, it's not mystical. In fact, now, medical researchers, for example, are doing work in analyzing breath patterns, other patterns to diagnose different kinds of, let's say, pulmonary disorders. But based on that, she would diagnose people and she would combine, talk about pharmacy, multi-combination pharmaceuticals to give different people. So not everyone got the same herb or the same mantra or the same massage. People were given different things. In fact, in the traditional system of Indian medicine, not everyone did the 22 asanas that you would go take at Bikram yoga, okay? The teacher would give you particular asanas because obviously if you had hypertension, you don't want to be doing certain asanas. So it was all tuned, and it was what we call personalized medicine. And again, it was based on this whole system. And if you look at the history of India, many of these guys in saffron robes or these robes weren't really just religious people, which has frankly been lost in the last 300 years. But they had a lot of, in fact, there's a lot of palm leaf manuscripts now, about 100,000 of them, which have been rediscovered by the central government. And these manuscripts are interesting because they're written in poetry, very sort of an iambic pentameter type poetry, which has the apparent meaning, but within that is sort of formulations. For some reason, these siddhars, as they were called, gave poetry as a way to hide. So you have to decipher the poetry. And there's a whole lineage, you can go read about it, but there's a whole lineage that goes back to where, these guys were really focused on medicinal, not only medicinal treatments, they did what we would today call nanotechnology, use of heavy metals, for example, arsenic, mercury in certain cases. But there was martial arts, but it was not just one system, but it was an integrated system of medicine, herbs, asanas, etc. So I grew up around this, but I also grew up around something else. India has a caste system. I don't know if you're familiar with it. Many Indians will not talk about it here. You won't find a lot of Indians like me. I come from what's called the untouchable caste system, okay? In India, people don't want to talk about this because India is made to, in the Western world, you see a lot of very educated Indians come here. But the fact that my parents even made it here was quite significant. And in some ways, it's a testament to the American dream, what America does have to offer in its very positive ways. But the caste system is very hierarchical. It was originally based on the feudal system. And we can go to the history of it if you want to ask. It was really reinstantiated in 1657 when colonialism came as a part of controlling India. So my heroes, frankly, were not heroes like Nehru or Gandhi. My heroes were a little more radical, like Bhagat Singh, who forcibly wanted to kick colonialism out, or people like Crazy Horse, or people like Che Guevara. So my origins were a lot more revolutionary based, like how do you actually affect change versus accommodate suffering in the world. So when we came here in 1970, I was motivated in two ways because I had seen such differences that it didn't make any sense to me. Like, as a child, maybe later on you're told it's okay to have injustice. So that was part of what moved me. And the fact that I thought I was very fortunate to have made it here. So I not only was very good at athletics, but I also was reasonably good in academics. By the time I was 14, I had completed all my math courses by the ninth grade by calculus. And I was very fortunate in 1978 and 77, 78, there was a professor at New York University who had taken out a small ad in the newspaper, which my mom cut out, which said 40 students were going to get selected at NYU to study computer science in a very sort of military-like intensive program. So I was fortunate, and the guy's name was Henry Mullish, who's, I think, just recently passed away. But Henry was thinking way ahead. Remember, there's no software engineers yet. Still, a mainframe computer would occupy the size of this room. But he had the vision to realize that one day you would need software engineers, and America needed to start putting together a curriculum to educate those students. So I was accepted, and my mom would drive me to Newark Penn Station at around 6 a.m., and I take the train into New York. And if you've ever been to Greenwich Village in New York in those days, it was all drugs. It was very dangerous. My first experience was two bank robbers crashing out of a jewelry window. And but that's what I did, and went from 8 a.m. to 8 p.m. I graduated top of the class, and I was planning on dropping out of school. My parents were obviously devastated by that, but I got very fortunate because my mom was working at this medical school. This is in the heart of Newark, New Jersey. At that time, it was called the College of Medicine and Dentistry, which recently got put into part of Rutgers Medical School now. But in that school, there was a mentor that I met, Dr. Michelson, and Dr. Michelson was a Brookhaven physicist who had just put together a wide area network between Piscataway, New Brunswick, and Newark. Okay, so it was independent of the internet, right? It was his own network he put together. And he gave me a job. Initially, I was interested in medical research. And they had an affiliation with Montefiore Hospital, and they had some of the best longitudinal sleep data of baby sleep patterns. Babies actually have 6 patterns of sleep and the onset of apnea. So I was doing what you would today call big data. We're using computers to look at these sleep patterns and try to do predictive algorithms when an apnea would come up. And in fact, I ended up writing a paper on this. But while I was there, something else happened. Anyone over the age of 40 will remember in most organizations like medical colleges, every office had a secretary. In those days, women had potentially 4 opportunities: housewife, right, secretary, nurse, or teacher, right? But this secretary, if you look on her desktop, by the way, it's called a desktop, right? This is where the desktop is. There's an inbox, an outbox, folders. You see the paper clips. You see the typewriter. There's paper here, stapler also for attachments, and they put a carbon paper. And they put 2 pieces and you type, and that would be your carbon copy. And this was all the components of a system. It was called the desktop, but it was a component that was called the interoffice mail system. And she would type a memo up, and it would literally look like this, by the way. It was very structured. It had memorandum, to, from, CC meant carbon copy, BCC were those blind people who you didn't want others to know were BCC, just like today. And then you'd have the attachment, right? And this would get put into this thing called the interoffice mail envelope. You tie it, and they got put into these pneumatic tubes. I don't know if anyone remembers these. Okay? This was the email before email. Okay, this is how people collaborated. You wrote research reports, you would get a forward, you would check it off, and you'd pass it off to other researchers. And this was a collaborative medium, all done through paper mail. So I was given this opportunity, because I'd gotten pretty good at writing code, to convert this to the electronic version. And I called it email. This is in the Smithsonian now. It was not an obvious term in 1978. No one had ever used this term before. The only reason I chose it was because of Fortran language. By the way, everything had to be in uppercase. 6 characters. The operating system only allowed 5. So program names like app names could only be 5 characters. This was not a simple system. It was a whole system. It had to be easy to use. Remember, secretaries, most people at that time didn't think a secretary could even touch a keyboard, right? They were relegated to the typewriter. It had to be easy to use. It had to work. These people were used to using the interoffice mail system. Doctors would tell me, well, we're never going to use that. I love the way the old system works, because all they had to do is go dictate, right? And a memo would come out. And this is one of the early pictures that came out in the local newspapers. Now, here's the interesting thing. Let's talk about intellectual property. In 1976, the Copyright Act of 1976 existed, which allowed you to copyright, like a play, a script, a novel. No one knew what software was. Like, what is this? It's like paper coming out, right? It's like text. It was much later, so the United States Patent Office wasn't recognizing software. However, in 1980, the the Computer Software Act of 1980 was passed, and was an amendment to the Copyright Act of 1976, which said that you could protect software inventions through copyright. So I had gone to MIT in 1981, and I was elected student body president, and I was at the president's office, and Paul Gray said, Shiva, it's unfortunate the Supreme Court still doesn't recognize software patents, but you should copyright it. So that's what I did. We didn't have lawyers. This was, I think, when I was 16 or 17, wrote away. So it's email, computer program for electronic mail system, and I was issued this on August 30th, 1982, by all legal definitions, recognizing me as the inventor of email. Okay? But the real thing that the reason I'm bringing this out is because email was a system, and I learned how to put together a large-scale collaborative system with all of its features. You have to teach people how to use it. You have to bring on board people, all the things we have to do whenever we bring on a new system. But that's what email was a system. It wasn't just a simple exchange of text messages. So I went on to MIT, but remember, I had this deep interest in medicine. So I remember signing up for my electrical engineering class, and they had a whole biomedical engineering program. But part of me sort of really distasted the way we looked at medicine. We looked at the body as a bunch of parts, right? Not as interconnections. And in fact, when you go to get any type of diagnosis today, if you have a headache, you may be sent to 4 or 5 different specialists, right? A neurologist, whoever, right? And you may come up with a pile of medication. And this never made sense to me, because I remember how my grandmother looked at people. She didn't look at people as individual people. She looked at them as a whole. So in my gut, none of this made sense. And for me, it looked like the old Buddha story, where the king brings in the 6 blind men. And it felt like biology was like these blind men who do great stuff in understanding maybe their parts, right? And biologists have to be what we call reductionists. So they understand their parts really well. But if they were to put it together, you'd end up with something like this, okay? It has nothing to do with that whole, but they may be really good at assessing the components. And as you look at this, what really gets a little bit depressing is that a lot of this is because it is reductionist. Biology has to be specialized, right? Because you can win a Nobel Prize for just understanding how 2 proteins interact. So you get a lot of incentives for doing that. And you don't get a lot of incentives for collaborating, because you have to get your funding, you have to get your papers written, and that isn't really supported. And so you don't look at it as the interconnections, you look at it as the parts. But a lot of this started changing. After I did my degrees, by the way, one point I want to make you aware is I've been working since I was 14 years old. Even when I went to MIT, I had a full-time job. I bought my first house when I was 17 years old because I didn't want to pay rent. So I'd always had this attitude of academia was one piece, but I was always working full-time. So either I would go to MIT, had a job, or I would start another company. So I'd done about 6 companies. In 1993, I had a second life with email. It was very fortuitous. I was in my PhD program, very interested in AI and pattern analysis. And I was developing a whole assortment of techniques to do analysis of documents, analysis of handwriting. In the middle of that, I got caught into an interesting contest with the White House when Bill Clinton was in office. 1993, if you remember, the web had just come out, and email moved from a inter-office intranet system into an internet system, right? Email existed before the internet. You don't need the internet for email, right? So when Clinton was starting to receive 5,000 emails a day, and he had interns, because you shouldn't use the word interns with Clinton, but he had students who would process email for him. They would read the emails by hand, and they would respond back manually. And the White House ran a contest to find out were there technologies that could do automatic text analysis. I ended up winning that contest as a PhD student and left MIT to start a company called EchoMail. We grew that to around $250 million in revenue. I made a ton of money, and my advisor said, Shiva, you should come back and finish your PhD. And what was happening was the genome project was just ending. And if you remember, the question was, what was the difference between a human and a worm? And the notion was that we knew we had about 100,000 genes, or we thought we had 100,000 genes. When the genome project ended, it turns out we had around 19, 20,000 genes, right? So this was really the time that I decided to come back to MIT. And the idea was you need to take a more holistic approach. Peter Hunter had just published this in Nature, which was saying, you know, the notion of systems biology, which was saying if you want to understand the whole, you can't just focus on the genes. You got to look at the proteins, and you have to be able to go across multiple scales and multiple spatial and temporal scales. So you have to take a systems approach, and it's not as simple as this genomics. So we have to move outside of the chromosome, outside of the nucleus, and we have to start looking at the whole cell. And 2003 was at a time when the National Science Foundation put forward this grand challenge: was, could you mathematically model the whole human cell? And so this is a very interesting problem, right? So in 2003 at MIT, the biological engineers and the people who are even systems biology were getting out of this, because to model complex molecular pathways, they were maybe doing 50 or 60 mechanistic pathways. The computer science people were getting into this because they said, we don't care about mechanism, we just care about input and output. So let me distinguish that just for clarity. There's two ways you can model the phenomenological world, right? You look at something, you look at the input into a system, the output, and you get data streams, and you do a correlation, right? You can use neural nets, you can use machine learning. There's a whole bunch of techniques. But that doesn't mean you understand what's inside that black box. But in biology, we want to know mechanism. But the mechanistic understanding gets too complicated because you have this much stuff going on. There's many tools which you can do these diagrams. So the issue becomes, how do you construct a way, let's say everyone here is in their own labs, everyone's producing pieces of that knowledge. How do you integrate that mathematically? And just to level set, this is what I mean by a molecular pathway, right? If you read the literature out there, they're called these ball and stick diagrams. So most of biology today is still diagrammatic, right? Every course, the professor gets on the blackboard and draws these diagrams. And behind this diagram may be 1,000, 2,000 papers, right? Every little reference is probably out there. But over the last 10 years, these diagrams are starting to move to mathematical models because we're able to measure with high throughput imaging the rate constants. Not saying that we're accurate, but these models are coming in different formats and different languages. So the issue is, how do you connect these models together? So assuming everyone here is domain specific, and you're owning models and you're starting to produce them, how do you connect them together? Because if you wanted to do this like this, it's an intractable problem, right? So we took an engineer's approach and we said, let's consider this blue circle representing some biological phenomena, or for that matter, the whole cell. How do you scalably create a system? And we said, imagine each of these pathways or areas of knowledge are going to be models at some point. They may be on the internet, and that's where we created Cytosolve. Cytosolve is a distributed system which lets you keep the models wherever they are, and it interconnects to them. It interconnects them together in a distributed fashion. It's almost like the orchestra leader in the sky. Now, we could create these models, or we could have systems of models and we connect them together. I'm going to share with you what we've done. But if email was the electronic version of the mail communication system, Cytosolve is the electronic version of the molecular communication system. We built a platform, essentially a collaboratory in the sky. So we ended up spending between, a lot of research work, and I'll share with you, we did the academic work, because obviously people say, well, biology is too complex, you can't model it, the literature may not be correct, all the sort of the things that we face in that. Articles like this came out saying we could eliminate animal testing, and this paper was one that really started making us realize that we really had come across something. This came out in Nature. Paul Workman was one of the authors, who I understand is a very noted cancer researcher. And this paper was saying that if you're going to actually solve major diseases like cancer, you can't just give a single drug. You have to do combination therapy. And we were the only ones cited in there as having a platform to really do combination hypothesis. And by the way, we don't know any of the researchers. We didn't call them up and say, please cite us. So we knew we had something here. And then we raised a little bit of money for Cytosolve. And I'm just going to give you sort of a fun example to start with, and I'll come back to this. But, again, going back to India, you'll see these yogis doing their mixing. They're the local pharmacist. And an interesting example of this is If you look at all of Asia, Asia means India, China, Indonesia, that whole region, the number one source of death in Asia is liver cancer. But it turns out Indians epidemiologically get 1/3 less liver cancer, and the epidemiological results purport that it's because of curcumin, high consumption of curcumin, which is the active ingredient in turmeric, which is the main herb, or one of the main herbs, depending on which village you are, in curry, right? Curries are actually very village-specific, believe it or not. And in fact, family-specific. People make their own curries. You could start a riot if you, attack someone's curry. But what we did was since this kind of stuff started coming out, there's about 6,000 papers now in PubMed. So we mined every paper using cytosol. This outer circle is a cell wall, the inner is a nuclear wall. What you're seeing is all the places that curcumin inhibits and interacts within the larger system inflammatory response. And then we did this actually as a fun exercise and where resveratrol interacts. And the reason we did this was I've always been fascinated with the supplements industry. A lot of the stuff is snake oil. A friend of mine owns a very large supplement company and he sold it. And I asked him, Paul, how did you come up with these formulations? He goes, oh, well, a Chinese doctor told me. Right? So it's always some hand waving, right? You can never get to, well, how did you figure out these dosages? So what we did was we found all the places where resveratrol interacts, and we said, let's do some in silico experiments. So the far right column here represents a cytokine expressing inflammation. And you can see I'm not giving any curcumin, any resveratrol. That's a control. Then I just give curcumin 5 micromolar, and it drops from 0.15 to 0.05. Same thing with resveratrol, a little less response. But this is where you get sort of the synergistic effect, right? I've reduced curcumin by 40%, this by 60%, and this goes down by 200%. This is an interesting case because in silico, I can start looking at that it's actually nonlinear effects. And from a drug development standpoint, this is what we like, right? We want to reduce toxicity, which means reduce dosage of individual components, but get synergy. And I'll come back to this because this was sort of their first thing where we eventually went into starting to look at much more complex diseases like pancreatic cancer, which I'll shortly talk about how we've taken that, we've modeled pathways, we've actually discovered a combo drug which got allowed by the FDA, and we've spun that off with MD Anderson, and we've actually spun out a company out of cytosol, and we're in fact doing that in many ways. But this sort of starts lending you to, hopefully start letting you to realize that if you take a systems approach, we use modern computing, you can start getting insights you can't without a systems approach. But remember, one of my real interests was still how my grandmother did these things. So in the Western world, this is how we look at, after you sort of got your PhD, this is your lingua franca, right? Genes, proteins, molecular pathways, regulatory motifs. But this is a way the Indian system looked at it. And I was very interested, could I bind both these worlds? So here I got my PhD in biological engineering. I somewhat studied this. And so I applied for a Fulbright. At the age of 42, people were interested, why does this guy with money, with his degrees, want to go back to India and study traditional medicine? So this appeared on the front page of MIT when I was graduating. There's a nice article saying but questioning why I wanted to do this. And so when I went back to India, I went back with an engineering systems approach. And I had a couple of ahas, but before I get you there, let me just sort of go through what is a system, right? This is a system. A system is an interconnection of parts where what emerges is greater than the sum of the parts, right? So, a watch is a system, but you don't really look at the gears, but it's the watch that emerges out of it. It's called an emergent property. Anyone know what this is? What is it? It's a space shuttle engine, okay? It's like an organ or something, doesn't it? You know what this is? It's a city, yeah. What? That's a cell, right? That's a robot. But anyway, these are different systems. So when you start looking at these different systems, an important question comes is, do all of these systems have common principles? So around the 1930s, people in cybernetics started looking at this. And the notion of, here is your system. All systems you find have 5 basic characteristics, what are called open systems. Input and output, very simple, right? But the other 3 interesting phenomenon that comes from thermodynamics theory is transport, conversion, and storage. We're looking at input or output, meaning information, matter, or energy. Transport is a notion of movement of energy, right? Transport in fluid flows, motion, In computers, right, it's a flow of information. Conversion is those aspects of a system that convert one form to another. And storage are the structural elements, or the things that give that thing the ability to store something. So you can think about the simple example of cooking at home in a pot. The ingredients are the input, right? The output is a bowl of soup you get. The stirring, right, is a transport. The conversion is a fire element. And the storage is a vessel itself. If you look at your computer, the input is a keyboard, output is a display. The storage is your USB drive, etc. The CPU is a conversion element. And the transport is a flow of information. What's fascinating is these principles are invariant. They occur in every system in the universe. This is called an open system, like a toaster you push on. But there's a more complex system that you would learn in your second course at MIT. It's called your control system, where you take the output, right, and you feed it back. And the notion starts with a goal. So an intelligent system, by the way, there's a book I have called System and Revolution, which I'll give you, because it really goes into a deeper, what does it mean to be an intelligent human being? The goal is, we start with a goal. So you have something you want to get. And the goal is, and in that model, you're feeding back the output. So a sensor is very important. And all of this is occurring in the midst of disturbances, but the sensor is giving you, hopefully, back accurately what's going on the output. The controller measures the difference between the goal and what you're really doing, and it sends an input signal, and hopefully you're changing the output, right? So you can consider the simple example of a thermostat in this room. We set it for 78 degrees. We're feeding back the output. The thermometer is a sensor. There's a controller here which looks at the difference. It lets hot water in or out, and the room gets warm or cold. This is a basic control system. You can look at an airplane, automatic control system, your cruise control system. But control system theory is the foundation of Western civilization, frankly, right? All the things we benefit from came from control systems theory. So when you look at, in control systems, you realize a goal is not like you just hit it, but you refine it, and you're constantly going in this feedback process, right? And this is sort of what makes it interesting. It's constant adjusting and sensing. When you look at the Indian system, what was fascinating, you may have heard these terms karma, right? Every yoga teacher uses it now, right? Or namaste, there's much other terms. But in the Indian system, when they look at someone's body, they have a systemic approach of looking at it. They look at your body, they characterize you as vata, pitta, or kapha, or combinations. So either they'll use it through pulse diagnosis, looking at your face, etc. But if you ask the average Indian medical healer, what is vata, pitta, kapha? They'll just do a lot of hand waving. And this is why it's been hard for Western scientists to appreciate them, because they think they're BSing them. Okay? So I was very curious about this. Well, what it turns out is, what I've sort of deciphered was karma. If you really look at the original term, it's not something spiritual. It actually means action. What is the action you take? There's actually another term called karma phala, which is the fruits of action. Okay? Vata is actually motion. Pitta is the forces of conversion. And kapha is the forces of storage. So when these ancient scientists were looking at a body type, they were actually characterizing these three forces, which varied in people at a meta level. More interesting, what it becomes is they actually had a control system. When you went to your guru, okay, he gave you your sankalpa, or your dharma, which was your mission. And again, all of this has been made very religious, to manipulate people. But originally, it wasn't that. It was a mission that you got. And the idea was that you would use your manas, which were your mind, as Buddha called it, your common sense. And you use your indriyas, which are your senses, touch, taste, feel, to understand the output. You would denote the differences, and you would take right action, which is what Buddha called it. Karma was right action, to get what you wanted. And the vikaras were disturbances. So in the same case, if you have a thermostat next to a window, that's a disturbance. You have to have a different kind of controller. So the net of it was, this is what I discovered, that when you put control systems here, and you put this here, that the ancient Indian yogis weren't really, frankly, yogis. They were basically system scientists who looked at the phenomenological world in a very different way from a control system standpoint. And when we put this out, we didn't publish it. I knew the medical journals wouldn't get this, and I didn't want to publish it in the alternative medical journal, so we published it in a systems engineering journal, because these guys got it. And the reality is that when you look at this, you start deciphering that they were looking at meta concepts, because it was too hard to look at this whole structure as molecules and genes. You had to develop, and control systems guys do know this, right? So I ended up, when I got back to MIT, the chairman of our department, I said, look, let me teach you a course. She goes, I don't think you can make it a course, but we did it as a lecture series. 200 people showed up every Thursday and Friday. We then took it online because I was a little bit entrepreneurial. We took the course material and made it an online course. We've now trained thousands of people through it. MDs, PhDs come to it. So in a room like this, I'll have an MD, PhD, and your woo-woo types of yoga people. Those people typically felt misunderstood by these people, and these people thought these people didn't know anything. But we've been able to bind these two worlds because when you go at it from this approach, it sort of makes everyone look at the world differently. So we made this into a course. We do this, and we also created an app called Your Body, Your System. And this is not to be a healing app, because I don't want to be a medical doctor, but what it does is it teaches people you can understand your body as a system. So you answer a set of questions, it figures out your homeostasis. It turns out this is transport, conversion, and storage. We figure out your particular homeostasis, and then we ask you from the epigenetics what's going on around you, and then it calculates how far you are, and it tells you a set of foods, vitamins, supplements that can help you get back to homeostasis. This is what my grandmother was doing, okay? So we sort of democratized the woo-woo stuff out of India. So you don't need your guru and you don't need to bow down to him because, frankly, that annoyed me. So that's my personal issues. And so that's what we've done. And you get this in an email. So what we've done is we've made it a tool so people can start understanding. Not if they want to use it for health, great, but that's not what it is. We promote it as a systems approach to understanding the body. But we could start layering other things into this. So that was what I'd done when I came back to MIT in 2010. After a lot of this, and I was serving in the Indian government, my advisor and I, we decided to spin off Cytosolve as a company. And we knew we were onto something because wherever we went, people were starting to get this. And I'll share with you some examples. I was giving a talk at Michael Milken's Faster Cures event that he was holding out in it was a small event, a retreat with around 20 to 30 neuroscientists. And I was sort of the non-neuroscientist guy, but I was the systems guy. And I was giving a talk about why don't scientists collaborate. And I said, look, we have a tool that'll help you collaborate. One of the scientists from the Keck School of Medicine, the head of the Neurological Institute, Berislav Zilkovic, was very excited. And he had come across the notion that most of the neurological diseases, or neurovascular diseases, if you look at Alzheimer's, ALS, they were all diseases that occurred probably 20 to 25 years before the onset of essentially holes or dysfunctions. We're looking at the lateral view of the blood-brain barrier. So if you think about the brain and the vasculature around it, it turns out that if that vasculature is compromised, you can have various types of illnesses. So here we're looking at a cross-sectional view. This tan here represents the endothelial, the red represents the parasites, and outside of it is the astrocytes, the quote-unquote brain. But the parasites are control valves. They determine, right, what blood flow goes in and out. And the theory was that breakup of the parasites could cause failure. So what we did was we mined all the literature out there using Cytosolve, and we extracted out the major molecular systems of the endothelial, the parasites, and the astrocytes. And then we proposed something interesting. We proposed an engineering systems architecture. Okay, so let's start looking at this very differently. So let's start with this bottom layer. If you look at this bottom layer, what you'll see here is this is the endothelial, and each of these little blocks in here are from the literature, the molecular systems that people have found through in vivo and vitro. We're not saying this is perfect, but from the known literature up until beginning of this year, you could map this like this, and similarly in the parasites and similarly in the astrocytes. So in engineering, software engineering, for example, you create layered architecture. So we said this is a foundational layer. The next layer we call the interaction or communications layer. In this layer between the endothelium and parasites, you see 3 or 6 subsystems of communication, and similarly with the parasites and the astrocytes, 2 subsystems. When we went through the literature and we started mapping the diseases now, we noticed something interesting. A number of these diseases, which we in Western medicine look at as individual diseases, are actually dysfunctions in particular communication systems from an engineering standpoint. When we submitted this, we submitted it to Nature, by the way. Half of the reviewers loved it, and the other half sort of were very angry and tough for it. Who are you guys? What is a computational systems architecture? It has nothing to do with neuroscience. It's all. Anyway, so we wrote back a 20-page response, and it got published. This just came out last year. So we're pretty pleased with this. Because it gives a whole different way of looking at neurovascular diseases, which says let's start looking at from an architectural standpoint, from an engineering systems approach, not even a systems biology approach. The problem with systems biology is there is no systems in systems biology. But engineers, what's fascinating about engineering is you can't sort of BS. Engineers have to build airplanes, otherwise they fall out of the sky, right? And in engineering, you go into it not just being academic and theoretical, knowing that you go into uncertainty like an entrepreneur, right? So you don't, yes, is this perfect? By all means, no. Neither was the Wright brothers airplane, but you can't tell that you can't critique the Wright brothers that they didn't build a space shuttle, right? But that's an armchair way of looking at this. What we are saying is we have a framework for starting to put pieces together. Another example, a critique that always comes around systems modeling is, well, you can't be accurate, right? It's too complex. But if the approach is right, our point was it can work. So this was another project we did for validation. This was between MIT, Harvard, King's College, and Brigham, where one of our researchers, Andrew Koo, Andrew was literally sending blood flow through an artery. Everyone knows Viagra, right? Viagra and O pathway. So Andrew was sending blood flow, and the blood flow on the surface of arteries, as we know, the mosaic on that surface, like your tiles at home, is the endothelial tissue, or the endothelial cells. What was interesting, if you look up here, this looks like a little Christmas tree. On the surface of endothelials, for many years, there was a lot of controversy whether the glycocalyx even existed. But it turns out that it does exist, and it's a mechanotransducer. That means mechanical energy gets transduced into chemical energy, or chemical motion. So when blood flows, the glycocalyx actually initiates a whole bunch of chemical response. So Andrew had taken him 3 years to set this up. He could do the shear flow, and he could measure NO. But if you look at the literature, you will also see all these different ball and stick diagrams. Everyone has their narrative, right? Like the blind man on how NO is produced. If you try to ram all these together, you can do it diagrammatically, but how do you do it computationally? And remember, any one of these pieces could be changing. New research could be coming out. So Andrew approached us, and we used cytosol. So each of these pieces, and there's others, were treated as components. We modeled them and validated them because they were easier to deal with the small pieces. And then we interconnected them. So what I'm going to share with you is quite impressive because this is not a curve fit. This is not big data. This is actually mechanistic results. So here's time, and we're looking at eNOS mRNA concentration. This is our actually dynamic curve, and that's the actual results. Okay? So you can do this kind of stuff. It's not unfeasible to get accurate results. And this was published in Cell's Biophysical Journal. So, and it's been cited very well. Our point is that if you break these into smaller problems, you treat them as engineering components. In many ways, we're reverse engineering it. The core of this platform has been since then used for looking at toxicity. We did a paper with the USP for soldiers who are taking multiple supplements. Yes, you can do it heuristically, but it doesn't get you. But we've been, if you want to get this and you want to send it to you, I can. So that's all on the academic side. Then people say, show us something you've done commercially. Alnylam is a company started by Phil Sharp, who won the Nobel Prize for siRNAi, silencing RNAis. So Alnylam is a company that focuses on, essentially inhibiting mRNA. So forget trying to hit a receptor, right? You try to actually suppress the mRNA. So they were working on a disease called hereditary angioedema. When we came in, they weren't even sure if there was enough literature. So in 45 days, we mined the literature. We found a high-level description. By the way, I can't share some of the mechanics for confidentiality reasons, but there's a protein called bradykinin that gets metabolized, which creates edema. It's a horrible disease. And then we modeled it. This is the target. They had actually gotten to a point in their research, preclinical, they'd been able to model this particular target in mice, but they were diffident to take it to clinical trials because it was counterintuitive to what everyone else had reported. So this is the protein, this is the target, and here's the protein. This is our prediction. After we did this, then they shared us their mouse data. Okay? So this is after the fact. So you can see how well our model predicts, but the more important thing is not just a prediction, they were able to understand mechanism. In drug development today, by and large, people sort of shoot a bunch of things out there, a duck falls out, and then they go try to explain it. It's really rationalized drug discovery. So here, we were able to give the mechanisms, and they were kind enough. This is probably the best thing we could get, which is Alnylam's in vivo study confirms cytosol's in silico predictions. Right? This is sort of your stellar case study. And finally, I'll give this other example, and I'll wrap up, is, remember I told you this paper that had come out. So when we did this, we did that fun example, But then we did something more interesting. We raised about $1 million, and we convinced our investors, we were only 7 people at the time, we said we would, in 12 months, we thought we'd be able to take the 200 some odd cancer drugs, find a bi-combination drug that did better than gemcitabine, and we said we'd also get an IND allowance. And we'd never done any of this. So entrepreneurs are like that, by the way. If you read Hoffman's statement, as someone who jumps out of a cliff and then builds the airplane as you're falling. So, because you have confidence, because you're pretty sure you have it, but you just need some capital. So what we did was, we literally went through and by the way, there's many systems behind this. We modeled all the mechanism of apoptosis, cell proliferation. As you know, in cancer therapy, you're trying to upregulate apoptosis, downregulate cell proliferation. And we modeled around 50 different integrated models. We honed out of the 260 to around 13 ingredients that can be given IV, GMP, all that good stuff. And we found 10 million potential combinations, 78 that were viable, 5 we optimized, and we found 1 bi-combination candidate. We applied for our IND through the FDA. We hired a toxicologist and a chief medical officer. And we got a call about 90 days into this from the FDA. It was very interesting. We thought they were calling to yell at us or something. And they said, we're actually fascinated by what you guys have done. This is what Janet Woodcock's vision is in the 23rd century. So it got allowed. What we did was, so we knew we had Cytosolve as one company. We decided from a business model, we've taken these mathematical models and the discovery, we put it into a new company, and then we went to MD Anderson, because by no means are we cancer. That's not our domain expertise. So we have now the best guys in the world in cancer who blessed our models, and they're in the midst of adding stroma and other more complex tumor environment, which we're going to get some very good results by the end of this next month on. And it's going to be a platform for in silico, in vitro, with sort of the credibility of MD Anderson. And we're starting to do this in other disease areas. We just spun out one in Alzheimer's with Harvard and ALS. And obviously, I'm putting this out there because Julie and I have talked about there's collaborations we can do now by using this, because we think what we've created is something pretty disruptive. And we can't do all of this on our own. So we need to do collaborations. So anyway, the one I'll end with as an example is this article came out in MIT in 2014, Buy Fresh, Buy GMO. I don't know if you know this logo. I don't know if you guys have the local movement here, like farm to table. This is actually a joke at the Buy Fresh, Buy Local. And I like buying local, and I was a little bit perturbed by this because it didn't seem like it was really Technology Review is known as a good science journal. And as I read through it, it wasn't that great of an article. It seemed like it was more an ad for GMOs. And I'm not pro or anti. But as you read it, you find out there's this huge debate going on, right? There's a very emotional debate going on. And the issue is, we wanted to find out, is there a middle ground to this? As you look at this, you find out that most of the debate centers around what is the difference between a non-GMO and GMO. This is sort of, is there a difference? Because if there's no difference, why is anyone yelling and screaming? And if you unravel this history a little bit, it's like asking, is there a difference between the Hulk and what is this, David Bannon, right? And the way we got to where we are today is there was a law that was signed in 1976 by Gerald Ford called substantial equivalence. Anyone aware of this? So substantial equivalence came out to really accelerate innovation. So if someone was, let's say, creating a stethoscope or someone who created 7 years to create a stethoscope and got all the FDA approvals. Let's say someone said, I'm just going to make a little change. I'm going to paint it white or some minor change. According to the rules then, even if you made a small change, it would have to go through whole FDA approval again. So substantial equivalence was a law or a guideline that Ford signed in, which just said, wait a minute, if this device is substantially equivalent based on some criteria, like color or something, that you don't have to go through this whole process again. You can fast track that innovation. Make sense? So, and as you read this law, when Michael Taylor, when Obama appointed him in 2000 to the FDA, they said, let's use this also for determining the substantial equivalence of genetically modified food versus an organic. Okay? And if you go through this, what you find is, and I've read through this, you find out that the manufacturer gets to choose the criteria. Okay? So you and I can start a GMO company. We get to choose color, water, fat, whatever we want to choose, and we compare it to the non-GMO. And if it's plus or minus 20, we can say it's substantially equivalent. And by the way, you don't have to share any of the data with the FDA. It's very loosey-goosey. It's all self-reporting. You simply tell the FDA that we did the research, and they'll send you what's called a safety consultation letter saying, thank you very much for doing the research. That's it. And with that letter, you can go sell your GMO. That's how it actually works, believe it or not. A lot of people don't even know about this. So we wanted to find out, what are those criteria? Like, what are objective criteria? So if you're going to compare two things, shouldn't you have objective criteria? Because technically, if you take a man or a woman and I say, I'm going to compare, do they have hair, 2 legs, 2 arms, you could say everyone's equal. But if you go at the chromosome level, you'll find something different. So what we did was, in a series of 4 papers, we did step-by-step. We used cytosol. And we did this as more of a fun project because we wanted to address this debate. So we took soybeans, and there were 6,837 experiments that have been done in 184 institutions in 23 countries. And these experiments were really looking at, let me sort of jump to this. So this diagram sort of represents the funnel. So this was, by the way, across 11,000 papers. So when we mined these papers, we found out there's a certain set of molecular systems in all plants that's called the C1 metabolism pathway. In that pathway, there's a certain set of subsystems that are invariant. Particularly, all plants actually produce formaldehyde as a part of methionine synthesis, and they actually detoxify it in the normal case. And we publish these papers, and you can get these online if you want me to send them to you, let me know. And we found out in the normal case, non-GMO soy, plants produce formaldehyde, and it's pretty rapidly detoxified. What we found out was, in the GMO, formaldehyde in our mathematical models actually accumulates, and the reason is that glutathione, which is a very important antioxidant, is getting depleted. When we published this, we got hammered in the press, as you can imagine. And I'll come back to that. People are saying, oh, this is just a mathematical model, don't believe it, it's not true. So we went back, and but remember, it's not just a mathematical model. We're actually looking at in vitro and vivo experiments. The molecular, A plus B reacting to get C is invariant, right? Sodium plus chloride gives already sodium chloride, but people seem to have forgotten science a little bit. It's not like we're just looking at big data. We're actually finding the molecular mechanisms and integrating them. So in this paper, we actually not only did the in silico analysis, but we were fortunate in Leeds in London, people had done in vivo in soy, and they had found that glutathione levels are 250% less in soy, GMO soy versus the organic. And that's what our results predicted. And by the way, to let you know that you can also being a scientist is not isolated. As you know, this deal just went through, right? And I was asked what I thought. And my position was, look, I'm not anti-pro-GMO, but we need to build safety assessment standards. And we need to take a systems approach. That's really the position here, because you're looking at a complex system. This is not a medical device. And, you can go look at all the stuff that's occurred. There's been a lot of very interesting issues about how academics at Harvard, for example, were mobilized by big industry to actually write articles that were literally told them to write. So this is a very interesting area from a science standpoint, right? And particularly where we are today in science, because what is truth and what isn't truth with social media, it's very, very hard to discover stuff anymore. So this, for me, was interesting because when this occurred, you start having to, I believe, as scientists, as graduates, you have to start looking at yourself as citizens now. You're not just doing scientists in your lab, but how is your science being funded? Are you truly a free scientist? An interesting movie. Anyone see this movie? Matt Damon, you should see it. It's called Inside Job. The guy who did this is actually an MIT PhD. He had done another company. He ended up doing his first movie and won an Academy Award. But what the movie was about was the 2009 financial collapse that took place. If you remember the whole economy collapse. And as you unravel this, you find out that he's interviewing this guy in the movie, and he writes this beautiful paper, right? Beautiful font. Looks great, right? Looks like a nice science paper. It says Financial Stability of Iceland. Well, 2 months later, the Icelandic economy collapsed. And he never told people that he was funded by the Board of Overseers of Iceland to write this report. And in his own resume, he had updated his resume to say, I wrote a paper on the instability of the Icelandic economy. It's a great movie. You should see it. He still has his job there, by the way. We all know the smoking facts, right? For 50 years, scientists said smoking was good for you. And Robert Proctor brought this up in this book, how this collusion took place. And probably the most biggest collusion was Galileo. He clearly had evidence the Earth is not the center of the solar system. He was vilified, and I think only in 1992 did the Catholic Church say that they made a mistake. It took 300 years. The reason I'm sharing this with you is, in addition to doing the science and all the other things that I enjoy doing, because of my journey, which may be different than yours, I've also been forced to ask some of these other social questions. The term military academic industrial complex, anyone heard of that? Right? I know it may be an old term, but for people in the 60s and 70s, President Eisenhower, in 1961, I believe his last speech he gave, he warned Americans and the world about the collusion between military and industry. And he said how it could destroy the world. Senator Fulbright, by the way, both these people weren't liberal politicians, they were Republicans, okay, which is fascinating, right? Fulbright basically gave a talk at a university called the Military Academic Industrial Complex, and the Fulbright Scholarship is named after him. And he also warned about this. For me, it's personal, because what I'll end with is this thing that is that in 2011, my mom was dying of pulmonary fibrosis. And 2 months before she died, in a suitcase, she had saved all of these documents from the invention of email. Remember, I didn't make a penny off inventing email, because you can make money off copyright. Had I been allowed to patent it, I'd be a gazillionaire now. But she had saved all of this, and Doug Aamoth came to my home, and he wrote this article called The Man Who Invented Email. He was the first journalist who spent literally like 3-4 weeks looking through all the material. After this, the Smithsonian contacted me, as Julie said, and it went into the Smithsonian in February 16, 2012. And a young Washington Post reporter wrote this on the front page saying, V.A. Shiva honored as the inventor of email. Now, you would think this should be a great day for celebration, right? But what happened, within minutes of this article being written, I had woken up some devil out of somewhere, and these articles come out. Imposter, people calling me all sorts of 4-letter words. And this invigorated vitriol all over the internet. People saying this curry-stained Indian should be beaten and hanged. I'm being serious. This is 2012. And worse. And I'm sharing this with you is because, my parents left India to escape the caste system. And what I found is, as you unravel this very interesting story, and by the way, the fortunate thing I had was I was also trained in political history. My mentor was Noam Chomsky. And I read Marx and Lenin and every history you can think about. So I could step back from this. And if I didn't, most people probably go into all sorts of depression. So I could step back as a political scientist and try to understand where this was coming from. And when you unravel it, you find this very interesting group called SIG-CIS. It's interesting. They call themselves Special Interest Group. A special interest group of historians who believe they own the narrative on the history of everything. And they had already written a history of email that it came out of the military. And these guys are in close collusion with Raytheon. Raytheon is one of the biggest military companies in the world. In 2009, they bought BB&N, which was a small company which did acoustics engineering, and they had rebranded themselves as the inventors of email, and they had a very nice-looking guy who looked like an inventor, okay? Doesn't fit the other narrative. You see what I'm saying? We'll come back to branded. But, I had worked with companies like Nike and all these, Phil Knight, so I had some experience in marketing. This is a beautifully branded page. Anyone have a marketing degree? This is what you call a beautiful logo. That's your brand logo, the @ symbol. That's your brand statement. We're the great innovators, and there's your brand mascot. This would be Michael Jordan, the Nike swoosh, and we're the greats in sports. So when my stuff went into the Smithsonian, I had thrown a wrench into this marketing campaign, a multi-billion-dollar wrench. This is a $70 billion industry. So if a 14-year-old immigrant kid in Newark invented email, what does that do to this brand, which claims that it is the inventors of email? Remember, these guys compete against General Dynamics, Lockheed, and cybersecurity grants. So what was fortunate was, because you're trained in science, I had a very good student. And when you're attacked like this, believe me, you think you actually did something wrong. It's like people I've talked to have been raped. You actually think maybe you did something wrong. But we went through every piece of literature written prior to 1978. We found this document in the bowels of the MIT microfiche, written by this guy, David Crocker, who was attacking me in the press, purporting to be the most expert in electronic messaging. Written, interesting enough, in December 1977, 6 months before I started inventing email. Look what he says. At this time, no attempt is being made to emulate the full-scale interorganizational mail system. The fact that the system is intended for use in various organizational contexts and by users of differing expertise makes it almost impossible to build a system which responds to all users' needs. Now, why was Crocker writing this? Because these guys were your old guys in white lab coats and big mainframes who were doing simple messaging. The thought of a ordinary woman office worker secretary using a computer, which is what that meant, users of differing expertise, was inconceivable to them. But for me, I thought them as cool people, and I didn't think it was impossible. Because I knew we had computing, I knew we had programming languages, and I knew that system. So anyway, we published this, we created the inventor of email site, and they started attacking us for being self-promoters. Right? They had a multi-billion-dollar machine behind it, but when we created a simple site, Chomsky came out, the only academic to come out on this. And interesting enough, in the midst of this controversy, this book comes out written by Walter Isaacson, a very eminent liberal historian, and it's called The Innovators of the Digital Revolution. This is in the middle of this heated controversy. And this is what I want to share with you. Now tell me what you see. Who are the innovators of the digital revolution? You see a pattern? And by the way, I've never played the race card in my life, right? So don't anyone take this the wrong way, okay? But this is an interesting pattern. And what's really exposes this pattern, he ends this by talking about Vannevar Bush, who was a president of MIT in the 1940s, who was one who created Raytheon. Okay? And all of the credit is attributed to this triangle, which he calls the golden triangle, the military-industrial complex. You see, I was a part of that while I was at MIT, right? Being a good minority, a good Indian. But that Indian doesn't fit that brand. You see what I'm saying? It doesn't fit that gated community. And I'm telling you this in a very sincere way, not to compel any. The issue is, as long as I was at MIT, I fit that narrative. But that 14-year-old kid doesn't fit this narrative because it sort of takes away the branding of where innovation comes from. And that's really the heart of this, what I'm trying to share with you. The fact is, innovation can occur anytime, any place by anybody. It can occur at MIT, but it can occur in Newark, New Jersey. And Peter Thiel, I don't know if you know him, Peter, who runs PayPal, talks about this. He says, look, we did the Manhattan Project in 3 years, albeit we built an atom bomb, right? And we can't seem to do a lot of things because we think we need all this stuff. So, by the way, this is this is at 81. When I came to MIT, it talked about students, 3 students who came, and it talks about this kid who invented the email system. All right? So the net of what I want to share with you is that, we do have a caste system still. And it's not a caste system just of money, but it's of attitude. And I think that's a big opportunity, and I think America's a place we can break that up. And by the way, in this article that came out, that's my mentor, talking about the invention of email. This is back in '82. What's interesting, I was reading this article, and it's fascinating. Next to the article, there's an interesting thing in here about preventative medicine and community health. Okay? The fact is, email did not come out of the military. It came out of a health sciences institution where collaboration takes place. Military is, command and control. That's text messaging. But email is collaborative. And it can only, and it makes sense, right? It only should have come out of a health sciences institution. And, there were women behind email. My grandmother inspired me. This woman was an independent studies teacher. She's the one who forced the Livingston High School system to change the rules so this 14-year-old kid could travel 30 miles and work at that institution. And obviously my mom, but also those secretaries. So I want to end by saying, so what does it mean to be an entrepreneur? I think that's part of what I hope to inspire you is we think it comes from this French word, right? If you've looked at it. But actually, if you look back in the old Sanskrit, there's a word called antaprerana. Antaprerana. Sounds very similar, right? And it means driven by insights. It's about 3,000 years old. And if you actually go read the text of the poem where it comes from the Brihad Upanishad, it says, you are what your deep driving desire is. As your desire is, so is your will. As your will is, so is your deed. And as your deed is, so is your destiny. That's what it means to be an entrepreneur. And if you think about the denial of a 14-year-old kid in Newark inventing email, it's not really about me, but it's denying the fact that each one of us is an infinitely divine human being capable of probably anything we desire, that goal that we set. And you don't need to go to MIT, you don't need to go to Silicon Valley, that it can occur anywhere. Because innovation and creativity is ultimately what I believe it means to be a human being. And, so I always end when I do these talks with students, I like to share what my 7 sort of elements of innovation. First of all, it's in our DNA. We're not that different than each other, We're not that different than gorillas, frankly, right? But we're not that different. The other thing is, it's really important, I think, to have a mentor. I was fortunate to have had Dr. Michelson. It's important to identify a real problem. It's not theory. I was trying to solve a very particular problem. It was very tedious for these secretaries to do this whole process, right? It used to take days just to type up a carbon copy. You had to do 10 carbon copies. It was a very tedious process. I had to find a customer. I actually had a living customer, and it was about serving them. You have to build to scale. Whether it be email or cytosolve, it's not one molecular pathway. In fact, if you read our first paper, it's called a scalable system. Which means we have to be able to integrate multiple pathways, many customers. You have to be able to create systems that are easy to use and scalable. Probably from a business standpoint, you have to protect your innovation. I was lucky. If I didn't have that copyright, right, I wouldn't even be here sharing the story with you. But the last thing I learned more recently, you learned it as an entrepreneur, but you have to promote your innovation. When I started promoting it, people started calling me a self-promoter. But I had to get over their attacks, to realize, wait a minute, I have every right to promote my innovation. In fact, it's my duty to do that. So what the net of I want to share with you is the beginning of this year. For years, when Gawker Media wrote all that vituperative vitriol, I couldn't find any lawyers in Cambridge, even to Boston, to sue them because everyone had conflicts. But the beginning of this year, if you want to talk about sort of where brains and brawn come together, Hulk Hogan, the wrestler, filed a lawsuit. I don't know if you know about this. And he won in a Florida court, by the way, jury. $140 million settlement because Gawker Media put up a video on him. I approached the same lawyer. They filed a lawsuit on my behalf for $35 million. 30 days after Gawker Media went bankrupt, they sold their company to Univision. Univision, the executives had a board meeting on the eve of the sale, which was last week, and they pulled down those 2 articles. And likely I'll probably get a settlement, but which I plan to put into my innovation organization to fund innovators. But at the end of the day, what I'm trying to say is the journey of being an innovator and entrepreneur is a fascinating one, and I believe each one of you has one. So, I want to impress on you, embrace your journey. It doesn't, collective stuff is really important, but look at your own journey, because within that is a very inspiring story for all of us. Thank you. I went over time. I'm sorry.
No problem.
Yeah.
So we've got a reception outside,
okay.
So people can talk to Shiva. But any quick burning questions?
Yes.
When you do your modeling, integrated layer modeling is the hierarchical kind of setup, right? So you use statistical modeling or actually solve the numerical equations for the output.
So what's your question?
You have layers of modeling,
right?
The modules and combine and that whole output to simulate for the simulation. So it's inherent to the statistical model.
Okay.
Or analytical.
Yeah. So this is more analytical. So if you look at so just to level set, when I look at biological modeling, there's really 3 layers of modeling. One is like molecular dynamics, where you're looking at 2 proteins interacting.
Right.
You're trying to solve Newton's equation, right? Which is a very intractable problem. The next level up that is a system of molecules interacting, which is molecular pathways. Above that, you have like pharmacokinetics and pharmacodynamics, right? We're literally at that middle layer. That's the area. We're like a molecular pathway model. But within that, you could do that 2 ways. One is statistical approaches. We're actually using a mechanistic approach. We don't use statistics there. If you want to think about where you could consider a rate constant, right, a statistical measure, right? But beyond that, we're actually looking at the mechanisms. So what's important about it is when people are doing drug discovery, they want to understand mechanisms. And it has some very interesting areas in intellectual property because you can't patent, for example, 2 known molecules coming together, but it turns out you can patent non-obvious molecular, pathways that can inhibit some very interesting opportunities for legal profession. Yeah.
So I'm just curious to know whether you use your system pharmacology, electrical system, biology models for understanding disease progressions, rather. Looks like from your discussion or your explanation that you're using this for more kind of drug discovery rather than understanding the pathophysiology of complex diseases. Am I understanding that right? Or?
We're actually doing both, right? So, for example, with Alzheimer's, right? So the approach we take is we look at the literature and first we say, let's get an engineering architecture, right? Which means let's understand all what we know of, at least what this architecture looks like. Because that starts giving us an idea of sort of drug progression etiology, I mean, not drug, disease progression etiology. And we get domain experts to actually review that. The next step after that is where we start, or sometimes we do it in parallel, is to look at how particular drugs or combinations work. But part of the architecture development is you're actually understanding the etiology of the disease. The other piece of that progression is, in traditional medicine, they say all diseases go through 6 phases. So part of this is the right medicine at the right time. So we're starting to look at how certain diseases progress, and that certain medications in the early stage do not work in the later stages. And also, temporarily, that when you're giving drug combinations, that if you give one drug first, the temporal way that you deliver drugs is also very important. We can start looking at those models also. So I'm trying to say the time rate of change of how disease progresses is a separate part, but we also do that. Thank you. One more? Yeah.
Very impressive live and very impressive presentation that you showed. When you go back to your 7 points of elements of innovation, so I think I don't know, but from my perspective, maybe there's an 8th point you can add, and that's luck. We all, the greatest innovations in human history, I think, were derived by all sorts of luck. And so, what do you think? How much influence is all these elements?
Oh, that's a good point. But I think luck is a wave field that we create. What I mean is, when I was at this entrepreneur conference in India, and a guy wrote a book on luck. And he said you can actually create luck.
That's true.
Right? So luck is not something that itself is something lucky. You can actually create luck, right? And it turns out that if you do, he enumerated, like if you do these 7 things, you can actually increase the likelihood of luck. Right? So you could argue, so in my case, it was my intention, right? To want to go to that New York University school, right? My parents' hard work. So I would say that luck is something we can manufacture. By doing a certain set of things, you increase that probability of that wave field. So I guess you could add that, but I think it diminishes it because you could probably put another thing called how to create luck. Right? And it would probably go close to this. You have to put yourself in an environment where last door, when I was at MIT, right, I was watching this guy give a tour. If you've been to MIT, it's like a system of buildings all interconnected. And this guy was giving a tour to, I think his friends and family. He goes, you know why this institution creates more innovation than that institution down the street, going to Harvard? He goes, see, because I could walk from Mass Ave through these buildings, and I'll go through 9 departments. And it's true. Because of the physical way that you walk through, you're going to create luck. Kendall Square now at MIT has physically thought of that, and they've actually put the incubator, and they sort of shoved everyone into restaurants and everything, and they're sort of creating this environment to create luck. Right? Because the idea is you have enough molecules concentrated in one thing, something's going to result. You're going to increase some binding. You're going to reduce some binding. So. All right, thank you. Yep, one more. Garrett?
Very important level 3. So could you say how you choose your real problem that is not too big, that you cannot solve, not too small, it's not
The way I look at a real problem is if you have to have a customer. When I was in India, we started an innovation environment. So if you can't find a customer, you don't have a real problem. That's probably the best way to find out if you have a problem. We can talk about it more, but you have to have a customer. Is someone willing to buy what you're willing to make? All right, thank you.